following is an explanation of example 5.9 out of the textbook located on page 201. In this example, we're given a sample of diborane gas, B2H6, which is a substance that bursts into flame when exposed to air. This sample has a pressure of 345 torr at a temperature of negative 15 degrees Celsius and is contained within a volume of 3.48 liters. If we change conditions such that we increase the temperature to 36 Celsius and increase the pressure to 468 torr, what will the volume of our sample be? Now, we really don't have any way to gauge what our answer should be. If we just had increased the temperature, we should be increasing the volume. And if we just had increased the pressure, we should be decreasing the volume. So in essence, we're trying to figure out which has the bigger effect. This is another ideal gas law question, so we need to set up our ideal gas law, PV equals nRT. Except in this instance, I have a pressure that is changing, a temperature that is changing, and a volume that is changing. The only two variables that I'm given that remain constant are n and r. So as with before, I'm going to go ahead and rearrange my equation to get PV over T by itself and n times r by itself. As with before, we have two different times. We have an initial and we have a final. On the initial side, we have a pressure, we have a volume, and a temperature. Our pressure, I'm given the pressure in torr. However, since I'm given the other pressure in torr, I can leave it in torr. And the reason I can leave it in torr is converting from torr to atmosphere is a multiplication and division conversion. And since all I'm doing in PV equals nRT is multiplying and dividing, those torrs will cancel out in the end. So my pressure is equal to 345 torr. My volume I'm given initially as being 3.48 torr, or 3.48 liters. And the temperature I'm given, now that is going to be a problem, because I'm given my temperatures in Celsius. And I don't like Celsius, because to convert from Celsius to Kelvin, I have to add. And adding and multiplying are not compatible. So I need to go ahead and change my negative 15 Celsius into Kelvin. Turns out to be 258 Kelvin. And my 36 Celsius, which is roughly body temperature, I'm going to convert, and that's going to be 309 Kelvin. So my temperature initially, we'd said, was 258 Kelvin. At the end, my pressure has been increased to 468 torr. I don't know the volume, but I do know the temperature, which is 309 Kelvin. That does not look like a K. 309 Kelvin. Now I'm going to go ahead and set up my PV equals nRT, but I'm going to use the PV over T equals nR version. And again, as with all other examples that I've done, we can identify that the number of moles, as well as R, do not change. So if these two values do not change, then my PV over T initially has to equal my PV over T at the end. So my P initial, V initial over T initial equals P final, V final over T final. I'm going to go ahead and plug in my values. My initial pressure is 345. My initial volume is 3.48. My initial temperature is 258 equals my final pressure is 468. I do not know my final volume, and my final temperature is 309. I just need to do a little bit of algebra and multiply by a reciprocal fraction on both sides, and I will get my answer. Be very, very careful when plugging into your calculator. Make sure you get the order of operations right, and we should get a volume of 3.07 liters. In the past, we've only had two variables that we had to worry about, but it is entirely reasonable to have three variables, where only one stays the same. As tends to be the case, the number of moles stays the same here. Almost always we're going to see the number of moles remaining constant. Again, this is example 5.9 out of the textbook located on page 201.